So now for this problem, we've been asked to determine whether the following series converge or diverge. And considering the section we're in, I might as well just say using comparison test. Of course, the type of test you're supposed to use will not always be given, but in this case, I think it's pretty obvious. Okay, so we need to think about a series that we could compare this series to. So that's the tricky part about all of this. That's the part that's going to make your head kind of spin a bit. Is you have to think about things you could compare the series that you have also to, and then think about what you know about those series. And the two big ones you know, of course, are P series and geometric series. So a lot of times we're trying to compare to those two because those are the ones we know about. All right, so let's start with playing around with this a little bit. I want to think, if this is A sub k right here, I want to think of a B sub k. Well, I'm not actually there yet. I don't have a B sub k, but I want to kind of play with it. That's what you're going to try. So you're going to manipulate, this is the way that I figure them out, and think, okay, well, I could go to k cubed over 2k to the fourth minus, not minus 1, over 2k to the fourth, right? That would work. Okay, so which one's bigger? Well, this one has the minus 1. Subtraction in the denominator makes a smaller denominator. So therefore, this is larger than that. Okay. But I know that k cubed over 2k to the fourth is equal to 1 over 2k, which is a half times 1 over k. Right? So these are all equal, right? They are one and the same. And I notice this one right here, so I think, okay, well, there's my b sub k right there. I mean, it's kind of both of these, so you could kind of say it's this one or it's this one. It doesn't really make any difference. So there's your b sub k, either this one or this one. And you think, well, do I know anything about that? So that series, so let's look at the series b sub k. That would be the series 1 over 2k, which is 1/2 times the series 1 over k. Right? Well, the constant doesn't really do anything. If you remember, we learned a property, and this is where those properties come in handy. We learned a property about series that basically says it doesn't really matter if you multiply by a constant. If it converges to that value, it's just going to converge to the constant times that value. So the constant multiple doesn't really matter for convergence or divergence. What's going to matter is what's happening to the series. Whatever the series does is going to win, and the half out in front doesn't really affect it that much. All right, so then what about that series? Oh, but that series is your favorite and mine, the harmonic series. 1 over k is a divergent p series. It's the special one called the harmonic series. So this is a divergent p series. And multiplying it by a half won't change the fact that it's going to infinity, right? It's p equals 1, right? It's technically the harmonic series. Okay, so let's think about this. I have a b sub k that is smaller than my a sub k. A sub k is, actually I should have written a sub k. A sub k is k to the third over 2k to the fourth, take away 1, right? So there's a sub k. Here's b sub k. When I think about that b sub k as a series, right, because these are the sequences up here, but when I think of this comparing the series, 1 over k is really the series I'm comparing to, and that's divergent. So I have a smaller series. Here, that's bothering me. It's smaller because the smaller denominator here, because of that subtraction of 1, smaller denominator, there we go, denominator, means the a sub k is larger. That's why the symbol faces the way that it does. So I took away the minus 1, which made a smaller fraction, larger denominator, smaller fraction. And then I, canceled. I divided and made things simpler. But I know that series right there. That series is the harmonic series, and it's divergent, right? And therefore, a sub k diverges also. It's an argument that you make. It's not really any one step along the way. It's the whole process, right? So you strip pieces out of your A sub k to make a different sequence. You hopefully can strip that sequence down into something more basic, and then hopefully you'll know what that is, like either it's a P series or a geometric series. Speaking of which, all right, let's look at this one. All right, so A sub k on this one is that piece. So it's n over n squared minus cosine squared of n. Interesting. Okay, so now we want to strip some pieces out of this. And what I'm noticing is that cosine. Let me just talk about that for just a second. Remember that the cosine of any value is less than or equal to 1 and greater than or equal to negative 1. When I square it, it's going to turn it positive, which means it's less than or equal to 1, but it's greater than or equal to 0. So n squared minus this value is always, oh, here, there we go. It's always between 0 and 1. You're subtracting something. In this one up above, we're subtracting 1 for sure. But in this one, we're subtracting some variable value that's somewhere between 1 and 0. So if I remove that, if I just take that piece away, like I got rid of the 1 up here, so that 1 was the part that went away. So if I get rid of this piece, just to kind of try to find something I can compare it to, what will I have? I'll have n over n squared. But if I get rid of that subtraction, then I've made the overall denominator, well, having that subtraction, let me put it that way, having that subtraction makes a smaller denominator. Which means that A sub k is larger again, just like it was on the previous problem, or previous portion of this problem. Okay, but n over n squared is 1 over n again. It's going to be the harmonic series all over again. All right, so b sub k would be equal to, well, b sub n, sorry. I'm not using k on this problem. And actually, I should have fixed that right here. Those are a sub n's. So this is a sub n. This is now b sub n. So the series b sub n is the series 1 over n, but that's the divergent p series, called the harmonic series. It's very special. It's the borderline between divergent and convergent and has a whole bunch of applications. And therefore, since the smaller series diverges, therefore the bigger series has to diverge also. And to be clear, when you're doing these problems, you have to show every step. You have to make the comparison, put in the correct symbol, show that the thing you're comparing it to is diverging or converging, and then go back. So you have to show all of this. This whole process needs to be here. You can't just take a guess at it and go like, it diverges. That's not how this works. So the writing of all of this is what you're doing. That is the problem. So you have to follow it in order. So you have to start with your a sub n, then your b sub n, make an argument to have the symbol go the correct way, then argue about whether your b sub n diverges or converges, and then reverberate back to your a sub n. Oh, shoot, a sub n, not a sub k. My fault. This particular problem is n. All right, last one. So for letter C, natural log of k over k cubed. Okay, well, here's where another theorem that we've worked with has come in very handy. Let me go find it in the notes real quick. In section 10.2, we learned that the growth rate of sequences has an order to it that matters to us. And that'll be helpful also for the comparison test, because the natural log of a value is significantly less than the power of that value, right? The power series of that value. So if you look at our particular problem, my a sub k, we're back to k on this one, A sub k is natural log of k over k cubed. And then I'm thinking to myself, well, I know that the natural log of k is significantly less than k. It just is because of the theorem 10.6. Okay, so let me make a little note. So, which is kind of explaining why this is. So the natural log of k is less than k. Right? Actually, I don't see the point in putting it over there. I'm just going to say right here, natural log of k is significantly less than k by theorem 10.6, and it was in section 10.2. And that's why this fraction is smaller than this one, because if the numerator is smaller, numerator works just like you think. If the numerator is smaller, then the fraction is smaller, right? So the numerator is smaller in a sub k. Is smaller, smaller than numerator in b sub k. Which is k. When your numerator is smaller, it makes your overall fraction smaller, and that's why this is going this direction. Okay. Tricky. All right. So, and that theorem, 10.6, is going to be a theorem you're going to use a lot to do your comparisons. So just something to keep in mind. The ones above on this page were kind of getting rid of subtractions and making things go away, but another thing we can do is just use the fact that we know how things compare. So that comparison theorem is actually quite important for us. All right, so now looking at our new series, b sub k. So if this is b sub k, but that's really 1 over k squared, is it not? I guess that's really b sub k. Technically it's both of them, but why would I write one that's not reduced? Really. All right, so then let's look at the series b sub k. The series b sub k is the series 1 over k squared. But that's a convergent p-series, because p is 2, which is greater than 1. Right? And since the larger series is converging, that will force the smaller series to converge too. So it's important that you make the correct comparison, you get the correct direction, and make an argument for that direction. Then you have to argue whether this series that you've made is convergent or divergent. And if you're going to do convergent, you need the series you've made to be larger. If you're going to do divergent, you need the series you've made to be smaller, right? So A and B, the new series is smaller, so those are divergent ones. C, the new series is larger, so that's a convergent one. If the new series diverges, it's useless, and you have to go back to the drawing board and find something else. If the new series is smaller and it converges, useless. Doesn't do anything for you. So you have to have the new series be smaller and diverge, or the new series be larger and converge. I'll actually make a note of that. So the new series b sub k is larger and it converges, as opposed to both of these ones where the new series and it's b sub n and b sub k, but you get the gist. B sub n is smaller, right? In both of A and B, it's a smaller series and it diverges. Those are the only two cases that do you any good for the comparison test. It has to be one or the other. If the new series is smaller and converges, useless. You have to go back to the drawing board. It doesn't tell you anything. If the new series is larger and diverges, useless. Doesn't tell you anything. So the only two cases that are doing you any good are those two cases. Which, looking back at the theorem, letter C is an example of the new series, right, there's the new one, is larger and converges. So this is type 1 from the theorem. And these two were both type 2 from the theorem.